Hi, this video is on installing the analog tools on a Mac. So let's jump to it. So it's a good idea to go to the tutorial. You'll find that in the description below. And then go to tools, and then you can read the text if you want to, but if you're impatient, just jump down to install the tools via xschem. If we open that up, that brings us to xschem, tells you a little bit about the tools, and then what I've done is I've made some scripts so that hopefully at least on a Mac and on Ubuntu 22.04 it should be relatively easy to install. So the first thing we need to do is to get xschem. So let's just copy that command. So this clones, well, xschem is short for Advanced Integrated Circuits Examples. I teach a course on Advanced Integrated Circuits, and the IPs that I use and the scripts that I use are all collected in the xschem repository. There's a lot of files in there, so it'll pull, when you do recursive, it'll pull them all down, and it'll also pull it down the Git repository for the tutorial. So hopefully that completes pretty soon. So in xschem there is none of the open source tools. It only has scripts to install them. So let's go inside xschem and we can have a look around. Actually, let's do it like that, or maybe even like that. So we have the license. I usually put everything under an MIT license, so you can do whatever with the files. There's a makefile. Let's check what that is. It's probably just to run some, yeah. So there's also a Docker example in here. However, let's actually make it slightly smaller. However, when I've used the Docker in my course, it turned out that most students have problems with Docker. On Windows 11, it didn't really work right, and so on. So I would actually recommend that you install everything locally. If you're on a Mac, then easy peasy. If you, or actually it's not easy, but it could be easy. If you're on Windows, then you should install WSL, so Windows Subsystem for Linux, and then install all the tools there. So what we're going to do now is, okay, so we need to add some options to my bash rc file. So let's open an editor and open bash rc. That'll be in your home directory. And let's see, I can copy this part, put it in. Actually, it's already there, as you can see, so we don't need to put it in, but you should add that. Let's go back to the tutorial. So after you've added those, you need to source your bash rc file again so that those settings are applied. You can check that with export, grep pdk root or pdk, and you'll see that variable is set. Okay, so if we now go into tests, now when you type make requirements, it'll try to install all the prerequisites that you need for the open source tools. Now this is going to take a while, so I'm going to pause the recording while that happens. And let me just pause there, and I'll come back when it's done. Okay, now it's done. So you can see it's using Homebrew, so you actually need Homebrew installed. Google Homebrew if you don't have that on your Mac. So one thing to note, it'll probably fail at the end here because I discovered that the libxft, that created some sort of conflict with I don't remember which one of the magic tools. So what I've done here is actually open a makefile, which we're running with the make requirements. And you can see here, make requirements, it'll check if you're running on a Mac or if you're running on Linux, or actually it'll assume that you're running on Linux if you're not running on a Mac. And if you're running on Linux, it will actually assume that it's Ubuntu 2204. Okay, so we can ignore this uninstall error because it didn't find it, and that's fine. That's what we wanted. The next thing is to install Tickle. Let's actually have a look in the in the makefile for TT. So TT will do TCL compile, so it'll download Tickle, the custom version that Magic uses, TCL 8.6, I believe. It'll install that, download TK, and install that. And you can have a look at what that does. So you can here see the TCL compile. It'll take the latest version from SourceForge and install that. So make TT. One assumption that is made in this install is that you have a directory called opt. Actually, let's go to that directory, where you can actually install stuff. So the default installation directory for the tools in this makefile is going to be opt EDA and opt share. Not opt share, opt PDK. Now that's going to take a while to get. I mean, it's downloading, not the fastest speed, and I don't think it's my internet speed. Actually, let's reduce the size a bit more so maybe it becomes possible to see the whole thing. So the nice thing about this is if Tim Edwards changes the Tickle version, it can be updated in the makefile. If I haven't done it, you can do it yourself just by changing the Tickle version here. So again, this is going to take a while to complete. And while we're waiting for that, I'll pause the recording again. Okay, so now it's mostly compiled, and it'll actually ask you for your password, because in order to install Tickle, you need to enter your password. And then you can continue. And let's see, yeah, so then it's installing, and you can see it's installing into opt EDA. And hopefully that part should be relatively quick. Now, I should note that for some reason, of course, it could fail. Maybe I've forgotten a requirement on your device. If you discover that, let me know. I might add it, but I must say I don't always have the fastest response time. The easiest way to get a change is actually to do a pull request. So fork the repository and do the changes that you feel are necessary and send me a pull request. And I'll happily review it. Okay, so now it's actually installed TCL, and now it's downloading TK. And actually, I don't know. So TCL and TK are pretty old stuff. I guess you could Google what they are, but Tickle, or TCL, Tickle, is a programming language. Really old one. And TK, I'm not entirely sure, but I think it's sort of the GUI-based version of, well, to be able to make Windows and stuff. And you'll find TCL and TK being used a lot on older Linux programs, and that's what xschem and Magic are written in. I should also note that most of the commercial EDA tools, they use TCL for doing, for example, digital on top layout. That there the programming language is TCL. I believe the same thing applies to Calibre, Calibre DRVs from Mentor Graphics. So learning TCL is actually a good skill to have, because at some point in your electronics career, you likely encounter it. And let me just pause again while we wait for TK to be installed. Okay, there we are at the end, and now you can see it's installed both TCL and Tickle. And I do a hack to the wish because I figured out there was a dynamic library change here that you had to do. So that's actually something that okay, maybe I need to source my bash RC again. TCL Tiki. Okay, that doesn't work, but Magic should find it. Okay, so now we get to the ADA tools. What we need to do is run the EDA compile. Now we could actually just do one of them, well, one at a time. So let's do that. Magic compile. So make magic compile. So magic compile will download the GitHub repository from Timothy Edwards, and it'll make some modifications to the setup files, and actually let's see what it does. Yeah, so we do some magic magic with Perl to the setup files. I think I had to do this in order to make it to compile on a Mac. And now we can see it's compiling, and it's checking, or actually it's not compiling yet, but it's checking the configuration of my Mac. And let me pause again. Okay, then magic is done compiling. So then we can do sudo make magic install, and it'll put magic into the right place. So once that is done, we should be able to start magic, and I can see if it works. That should be relatively quick. There we go. And there we can see magic. Wee! Starting. Perfect. Then we have magic installed. The next tool we want is, let's see, xschem. So same procedure. Make xschem compile. And note that here it will always pull the latest Git repo. It will pull main. So there could actually be that there's an update that is, or there's a version that is broken. In that case, you can always go into the Git repo and select a version. So for example, here, if I go to xschem compile, you could actually do, for example, git checkout, or yeah, checkout whatever version you wanted. But might as well, the tools these days, like xschem, magic, ngspice, they're getting quite regular updates. So it sort of makes sense to use the latest one and see if it works. If it doesn't work, then you step back one version and you use that older version. Now, I think xschem is actually relatively light, so it should be quick to compile. Actually, one thing I wanted you to note is that most of, I guess, both magic and xschem, it's written in C and relatively sort of old, not old, but blazingly fast programming languages. And there it's done. Let's do make xschem install. Okay, once that is done, we can check that it works. And there we go. Okay, the next tool you'll need is ngspice. Now, in the... Actually, let's do netgen first. That's even faster, I think. So netgen, that's the tool that we use for LVS. Netgen. Same thing, pulls it from the Git repo and compiles it. I wanted you to notice one thing. For the EDA compile, I actually run the ngspice compile twice. So there's something in the compile parts all the way at the end here, which is compiling ngspice that seems to fail for the first try. So I found that just running it twice for some reason fixes it. but I haven't figured out what yet. Anyway, it shouldn't take more time. Although ngspice is actually relatively heavy to compile. And let's do netgen install. Install. Jeez. Install. Okay. And we can check that that works. Yes, perfect. And then we want ngspice. So let's see if it fails. Again, it'll clone the SourceForge Git repo, and ngspice is relatively large. It takes a while to compile, as I said. I've also enabled xspice, Cider, PSS, and most importantly, OpenMP, which gives you multi-thread. I don't know. I'm not sure if it's multi-processor or multi-threading. Anyway, you can run, if you have a CPU with many cores, which pretty much everybody does these days, you can run faster SPICE simulations, which is a good thing. Also, note that in order to get OpenMP, you actually need to compile with GCC, so the GNU C compiler, I assume, instead of Clang or what's default on the Mac. Now, that should, I believe, be installed by the requirements. Let's see. Or maybe it's not. Okay, so it'll probably likely compile still, but if you don't get sort of the multi-threading or multi-processor speed in ngspice, then you need to install GCC and something larger than 12. Now, I know from experience that ngspice does take a while to compile. Let's see if it starts now. Hopefully it will. Same here. Oh, here you can see it failed. Now, if you just run it again, it seems to become happy for some reason. So there might be some sequencing of commands here that I haven't gotten right. If you figure it out, again, pull request or fork and pull request. Maybe for those of you that are not sort of deep into Git, if you go to my Git repo, and let's go to A6. So in here, you can always, well, I'm not able to fork, but you should be able to see oh, there we go, a fork button. So I can't fork it, but you can if you have a GitHub account. And then you can check out your own version of A6. You can modify the file, and once you've done that, then you can send a pull request, create a new pull request, and send it to me. And if you do that, then yeah, that's a good way, I think, of sharing the workload. So if you figured out something smart, well, tell somebody. make the world better. Because I sometimes have limited bandwidth, I think I want to say. And that also means I don't spend 100% of my time on maintaining these repositories. I have a day job. Actually, I have two. I have a day job at the Norwegian University of Science and Technology, and I also work full-time for Nordic Semiconductor, which means there's limits to my time. So I would be, well, any pull request with improvements would be greatly appreciated. While ngspice is now, actually, it seems like it's got going. So it went past the point that we stopped earlier. So, okay. I don't know why, but anyway, running it twice works. And now it's creating all the config files that it needs to be able to compile. And as you can see, ngspice contains quite a lot of components. So I'm going to pause again while ngspice compiles. Okay, then the compile of ngspice is done. So let's install that. Install. And it'll ask for password again. And this should finish relatively quickly. It's just moving some files around. Okay, and let's test it. ngspice. Yeah, okay, so we actually got version 40 here now. Cool. I had 39 before. Exit. Right. So let's go up to the... actually, let's go back to the tutorial. So now I've done all the EDA compile and EDA install. So I got xschem, I got magic, I got netgen, I got ngspice. Now I have quite a few custom scripts that I use, and you also need these libraries if you're going to use those. Make sure you have Python 3 installed. If you update your Python version, then you need to reinstall the packages. I think I use the homebrew version of Python because then I don't need to update that often. Mac OS has a tendency to just update the Python version, and then I need to reinstall all the libraries. So I'll download those. And while it's doing that, we can have a look at what's next. So the next thing we need to do is to install the PDK. So I have a separate script for that. It's called install openpdk, and we can have a look at that. So that will, first of all, it'll make the PDK directory. I've chosen to put it in opt-pdk. And it'll clone the Sky130 PDK, which is large. And, well, I should say that it's not a full Sky130 PDK, because I actually choose not to install all the libraries. So for this, most of the analog stuff that we do, you don't actually need the standard set libraries, which will make the timing part here go a bit faster. And then we'll download OpenPDKs, because Timothy Edwards, again, he has made some fixes to all the spice files and so on. So that's a good idea to run. Okay, so let's run that script. What did it say? Let's just copy the command. Okay. From memory, this actually took a while. Okay, so now it's downloading the IO library, and it's downloading the PR. So that's, I don't know what that actually is short for, but in PR you'll find the transistors and so on. And let's see, should we wait for this to finish? Probably not. It's gonna take a while. So I think the whole process probably easily takes an hour to download all the files and compile them. Well, I guess depending on the speed of your system, but it is a significant amount of data. Yeah, let me pause until something happens. Okay, now it's probably, what's it doing now? Alright, so it's installing Miniconda, no idea what that is. Oh, that's a package manager, right? So it's running actually a separate version of the tools and so on, I think. Yeah, installing base environment. Yeah. Yeah, let me pause. And for you, the time will go quickly. For me, it will go slowly. Now we can see it's gotten to... Oh. Right, so there's an error in my script somewhere. Interesting. Let me figure that out. Okay, I found the problem. So turns out that makedid on Mac doesn't have the parents option. So let's do it like that. And I don't think I actually need to run it again. Yeah, maybe I do. So I'll fix that, and then let's just delete the Sky130 PDK. So we check that it runs. Ah, good thing that I did this video. Found a bug. So I'm gonna rerun the script, and let's see if it fixes things now. Okay. So while it's doing that, let's check that it actually ends up in the right location. Yeah, now it's here. Yeah, okay, so now it's downloading into the correct location. So while that is running, I'll fix it on the GitHub. Okay, so now it's downloading OpenPDKs, and I think that actually, let's check. Yeah, so it'll download OpenPDKs next to the Sky130 PDK under the OpenPDK path. So the trouble with these scripts is that I tried to make them so they both run on Linux or Ubuntu 2204 and Mac, but turns out simple commands like makedir, they don't necessarily have the same options on Mac and Linux, so that's why it failed. And probably last time I tested this was on a Linux machine. Anyway, it's fixed now, and I think it should work fine for Linux also. But when you encounter errors, because there might be errors in my scripts, there might be errors in the open source scripts, you just have to try and read the error message and try to figure out what is going on. So now we can see the OpenPDK stuff happening. Bunch of fixes to spice files and a lot of things. For details on that, I guess you have to check with Tim. So while it's doing that, I'll pause again. We don't need to wait. Okay, so I think we're close to the end of the OpenPDK. Since it's asking for my password, hopefully. Let's see. One thing to note, though, is that it's a good thing to realize that once you have installed ngspice, xschem, magic, and so on, you actually have the code. So that means that if you wanted to do changes or figure out how something is done, you can actually just look in the source code. So you can go into xschem, you can go into source, and then you can have a look inside. Now, as always, reading somebody else's code is never easy. Okay, now it's done. Good. So let's go back to the tutorial. So now it also tells you to install CICconf and CICSym. And let me just show you how to do that. So those are actually my scripts. So I need to go to where I installed or where I cloned ASX. Okay, so if I go into IP, CICconf, and then this will install, it's a Python package, so it'll install that. And also download any dependencies. And CICSym, or as my students call it, xschem. And now we have that. So let's have a look at schematics, or let's actually check that xschem and so on works. So if we go into, there's a 9-bit SAR in here. If I go into work, and then I copy, let's check with magic first. Open that design. And I have to resize the screen a bit so you can see it. Okay, here you can see magic and you can see the SAR. And you can also see it's DRC clean. Now this is a compiled SAR, so it's actually not hand-drawn. Let's go zoom in. Oh, that was funky. Anyway, you can have a look at that. You can play around, but reading the layout, that's always tricky. It's much better to look at the schematic. Now, hopefully the new version of xschem actually is possible to show you. Let's see. I stored my design files in design, sun, and so on. Hey, I think you can see it now. The previous version of xschem actually let me switch colors. No, you can't see it. Crap. And then it quits. So I have something funky with my xschem. So every time I press cancel, it exits. I probably need to go back to an older version. Because, oh. Every time I press a button, it cancels. Let's see. What I wanted was toggle the color scheme. But you can't see that. You just see nothing. I can see a schematic, but you can just see text. I have no idea why. Okay, so it's not related to xschem version. Maybe it's related to how it's compiled then. Anyway, I can see it, so if you install it on a Mac, you should also be able to see it. But it's not that interesting to look at this. That's too bad. Okay. I think that's what I wanted to cover today. Actually, let's check one more thing. Let's check that simulation works. So let's go to the example. Now, the tutorial that I started to show you, where we found the tools thing here, you can also find a full tutorial on how to do schematics, how to do layout, how to do simulation. That is also a Git repo. So that's the path. It'll come as a part of ASEX. And if we look at the tags there, you can actually go back in time and start the tutorial where you would like to start, whether it's simulation or whether it's xschem or whatever. But let me just show you the final results. And rescaling magic again. So the design here is basically a current mirror with one input transistor and 5 outputs, which is not a good idea. So it's slightly asymmetric, but who cares in this technology? And we should check that ngspice work. So I rarely run ngspice directly, because one of the fundamental problems of running spice simulation is you never want to do one. You want to do temperature, voltage, slow transistors, fast transistors, and all the combinations and all the permutations. So that's why I wrote CI/sim. So in the simulation directory, sim Ripley, which is the simulation directory for the top level module, in the directory above that, there will be a setup file for xschem. Actually, that just links to the technology library that I made in tech. But that includes a bunch of options like temperature and voltage and slow fast transistors and so on. And as always, there's going to be a make file because I like make files. So when I write make typical, and let's show what that does. So first of all, it'll netlist my schematic because quite often you update the schematic and you forget the netlist, and then you simulate and you can't figure out why nothing has changed and so on. So it's always a good idea to always netlist. And then runs xschem. To take another example, if I do slow, you can also see that xschem has the ability to run slow transistors, and then you can actually give it multiple options for high and low temperature. So if I run those make slow, here it's going to take a while because just reading the spice files takes a few seconds in ngspice. But if you have long simulations, it's not going to be a big deal. So you can go through the tutorial and you don't have to check out the whole ASICs, but since you have the Ripley example already, you can just use the one in ASICs, and then as you can see here for the different tag versions, you can pick whether you want to start with the schematic or have the schematic ready and do a typical simulation or do corner simulation, or actually jump in and simulate directly on X, or just look at what the end result is. Okay, so there it run the first simulation. It's a current mirror, so it extracts the current in the output device, which should be 20 microamps, but it's not, because I assume drain source you get, well, the voltage on drain source is probably slightly different on the two devices, because on the output device I set a voltage source to control the voltage, while on the input device you'll have the VGS of the transistor because it's diode connected. So that gives you a slightly different current, which is quite common when this is a sort of a very simple current mirror. Maybe you'd add cascode to fix that, or even an active cascode to fix it. Okay, so now it's run both corners. I can then start ngspice. ngspice. It's getting late. And then do load, and the simulations will be put here in the output tran, and then the same as the corner. So let's pick the low temperature one, and you'll have, actually let's show all the files. So you'll have a raw file, which is a spice raw file. There will be a YAML file with the extracted results, and there will be a log of both the simulation and of the measurement. So I split the spice simulation process into two. I always just simulate in one ngspice run, and then in a second ngspice run I load the, actually let me show you that. So there's a second ngspice netlist that is generated. The first one is just a spice file. Actually we need tl spy. So this is the first spice file that xschem generates, and here you can see it loads the low temperature corner, and there's going to be a second file here called mess, where it loads that simulation, the low temperature, and then runs the extracted simulation. There will also be extracted simulation, extract the measurements. There will also be a temperature high, and the only difference, actually let's do diff. TL mess. You can see the only difference between these two files is that load line. But the reason I like it like this is because I can actually run ngspice directly here. So TL mess, and you can get the extracted results. You can do the same thing with the spice file, run it directly on the generated spice file. So that makes it easier to debug. You can change it if you want, but xschem is nothing other than orchestrating the permutations of all the different corners and then extracting, and it has a couple of options like I can also, if I change my measurement, I can do make slow and add an option for don't run. No run. And then it actually won't rerun the simulation. It'll only do the measurements, which is much, much quicker. In addition to that, it'll generate a results file for the simulation. So here we can look at slow. Oh, I need, I guess I need, which simulation am I actually running now? Let me check if I'm running layout. Yes, I'm running layout. So let's see what the latest result was. Okay, so that's that one. Let's open that one. Now, after the simulation, it will run a Python script. xschem does that automatically to generate an HTML page with the results. Okay, I think that's pretty much what I wanted to cover today. Sort of an introduction to how I install the analog tools. I hope you found it useful, and see you next time.